Okay, so today we're going to talk about some properties of graphs. So if we look at properties you learned about in grade 11, maybe earlier as well. You're right, one of those. Properties of graphs. Can you think of some properties of... Here. What would you say about this one? Yeah, it's a quadratic. What are some properties that we would want to know? Symmetrical, yeah, that's good. Symmetry, is it symmetrical? Yeah, for the parent function. Once you start transforming it, there is some symmetry, but we're going to learn about some other types of symmetry that are more specific. How about a line that does this? Give me an example of a property. It has slope, yeah, so it's not diagonal. Yeah, sorry, it is diagonal. So we've talked about domain, we've talked about zeros, y-intercept, symmetry. Some of the new properties. Does the curve increase or decrease? And you might say yes, you might say maybe. When would it be maybe? Well, look at that parabola that's on the screen. Does it increase? Always? Let's say if I start her and I go in this direction, is it increasing? What if I start her and I go in this direction, is it increasing? Okay, so then you'd say it would be increasing forever, right? Yeah, but what if I start her and I go this way? Now what? It's decreasing. Oh, well, we better find some sort of convention so we know what we're talking about, right? Turn left right here. That's confusing in a number of ways. Why? Why is it confusing when I say turn left right here? Left right. I do it all the time. After school, I go and I do exams at the at Serville. Serville? It's Canotech? Yeah. I fail them all the time. Yeah. No. So why is it confusing when I say left right here? Well, because I said both directions, right? But let's say I turn left here. Why is that confusing? Because I'm facing you. Whose left are we talking about? Yours or mine? Always mine. I'm important. You're not. No, so increasing, it depends on where we start. So where do you start when I say read this sentence? When I say to you, read example 1, where do you start reading? Left to right. Agreed? Unless you were in Japan or China. Maybe they go backwards. Is that right? Anybody know? They go down? Oh, so that's what I've been doing wrong. I should just take the Arabic menu and do that. Anyway, yes. So you have to go from left to right. So if you're looking at this curve and you want to know whether it's increasing, you have to start on the left. Well, can I start further left than 0? Yes. Can I start further left than this? Yes. Can I start further left than this? Yes. I would actually start, and I'm going to keep going, and I'm going to keep going forever. Do you understand? So if I start from there, and I start moving towards the right, what's my cursor arrow doing? Is it increasing or decreasing? Decreasing. So you would say, the curve is decreasing. What? Curve is decreasing? Wrong. Oh, it's decreasing sometimes, and sometimes it's increasing. Agreed? So we describe, when a curve does that, when it changes, we describe the intervals over which it increases and decreases. Fair enough? Does anyone want to take a guess as to what the increasing interval is for this curve? When does it start increasing and when does it finish increasing? Zakoots, what do you think? What? I'm not trying to get you. If you weren't listening, that's all right. Waffle, what do you say? Mm. The number 2? Mm. So you said from -2, and then you were pointing that way, so to that. That one? So from -2 over to here, correct? Okay, as I'm going in that direction, tell me when to stop. That's right. Yes, yes, y'all. And it don't stop because we're going to infinita. So you would say from -2 to infinita, right? And this is one way to say from -2 to infinity. You see what I'm circling here? Let me mark it up. See right there? That's an interval. It's saying x is greater than -2. Would you guys add a little whoops there? X is greater than or equal to -2? Why not? Exactly, it's doing nothing. Cool. So we don't include that. That's the interval. Well, you guys might want to learn this new nomenclature or new notation. This is part of set builder notation, and what we have right here is called interval notation. You see those brackets? You can use those brackets, or you can use these brackets like that. Square them up, yo. Square them up. Replace that. Round them off. Replace that. So if you're going to include the point, say -2, you're going to use a square bracket. If you're going to include the other endpoint over here, you would use a square bracket. But who can tell me where infinity is? Nobody. Why? Because it's not really a number, is it? It's kind of like an abstract concept. So since it doesn't really exist, then we never include infinity. What's the opposite of infinity? Anybody tell me where that is? Kind of abstract. Again, you don't include negative infinity. Do you guys understand what I'm saying? Okay, so that's for intervals. So let's have a look at this. Written in blue, it says the function f of x, which is the parabola, is arrow pointing up, means increasing. You can write the word increasing, and that would be fine. You could just say f of x is increasing on, and then you list the interval either this way or this way. Yeah. So if you wanted to include that point that's right there, normally you would, exactly. So to replace a greater than or equal to, you would make the bracket square instead of round. And then it would be, if it's less than or equal to, you would make that bracket square. Let's say you were trying to say less than or equal to infinity, then you would make it a square bracket. But since we can't include infinity, because it's not an actual number, we're going to use round brackets always for infinity or negative infinity. Yes, exactly, you can. I know, it's cuckoo, right? So, for example, if I were to draw for you a piecewise function, so here's your piecewise function. This one here, like that, okay? And then I might go like this. So, in this interval, the first interval is from negative infinity to, let's call that 1, okay? You're going to say it's increasing from negative infinity. Am I going to include negative infinity in my interval? Would I say x is greater than or x is greater than or equal to negative infinity? Which one? Correct. Why? Correct. We good? So that means if I'm going to write it in interval notation, I'm going to write it with a round bracket. Am I including an x value of 1 for the increasing interval, since the circle is open on 1, not including it. Can I include it in my second interval? So I'm going to go from 1 to positive infinity. Do I include positive infinity? No. So it's increasing over here and it's decreasing over there. Reasonable? Questions? Okay, so when you look at a curve, you can describe whether a curve is increasing or decreasing, but you have to list your intervals starting from the left towards the right. Good? And that's how you decide whether it's increasing or not. Next property would be, is the curve continuous or discontinuous? And that one is self-explanatory. Would you all agree? Does the curve have breaks in it? And y'all would have seen curves like this last year. The reciprocal function has discontinuities at vertical asymptotes. So it's usually at vertical asymptotes, or if there are holes in the curve, which we'll talk about how you get holes based on an equation later. Okay, that's the second property. Any questions? All right, let's talk about odd or even. Hello.
So on the graph on the left, how would you define where it becomes continuous?
Good question. So you'll start on the as far left as you can, and then you start moving towards the right. What would you say for this portion here? What's the curve doing? Is it going up or down? Okay. Now it's going up but less, but still up. So it's still up. Now?
Like if you had like a sine wave.
But that's not a sine wave. If you had a sine wave, every time it would stop, that would be the end of your interval. And then you'd have a new interval for decrease. And then it would stop, then you'd say, new interval, this time it's an increase. Yes, or you can list it using some sort of nomenclature or some symbols or terminology, which you probably did last year as well. Let me give you an example. You might say it increases from 0 degrees to let's say from 0 to 90. Okay, and then it's going to go again 360 from there. So at 360 to 90 more, so 450, and so on. So what you might do is from 0 to 90, and then what is that? 90 degrees, 90 degrees. So then you might say plus n times 360. I'm not asking you to do this. I'm just answering his question. N times 360 because it's periodic. Do you understand what I mean? So you could have this next to the 90, and you could have it next to the 0 as well. And then you would say n is an element of integers. So you're going to multiply 360 by 1, 2, 3, 4, or negative 1, negative 2, negative 3, 4. But don't worry about that for now. Okay, so y'all understand the difference between continuous and discontinuous? Right on. You need to be able to identify from a graph, that's easy, or from an equation, a little bit less easy. But what you're looking for discontinuities in an equation, you're looking for restrictions, okay? So any restrictions would be it's usually going to be discontinuous. Well, we'll talk more about that when we get to some more Challenge-ones, okay? Now, is a function even or odd? Remember when Chocolate Chip said that Zakuti was odd? Oh, I think the word you were looking for was unique. Now, it's all good. So, even, odd, or neither describes the symmetry of functions. Somebody said symmetry. You said symmetry earlier? So, if you look at a parabola, it has symmetry But some people might argue, well, not always. Well, the parent parabola definitely has symmetry, but something that has symmetry usually will say, well, that's defined based on a line of symmetry, right? So that's why we call the line that goes through, the vertical line that goes through the vertex, we call that the axis of symmetry. So a parabola has symmetry about its axis of symmetry. That's not always going to be the y axis. It'll all depend on what transformations took place. Do you understand what I'm saying? Well, this curve does have symmetry, and because its symmetry is about the y axis, we call this an even function. Does this curve here have symmetry? Does part of it look like a mirror image of another part of it? Yes, but it doesn't look the same as this one, right? Because the mirror line is here. You all agree? Okay, where's the mirror line for this guy? You could either say it's right there, or you could also say, oh, there's one right there, right? Well, if the mirror line is there, we say it's symmetrical about the origin juice, because what you've done is essentially rotated it 180 degrees. Or you could say you reflected it this way, and then you reflected it that way, so it's symmetrical about the origin juice. Okay? So those are two types of symmetry. Even symmetry, it's an even function, and this one is an odd function. We good? And I'm going to show you some tests so that you can tell whether or not a function is even or odd. If I give you the graph, can you tell whether it's even or odd or neither? You might say this one's even, this one's odd, and then you want an easy neither. Because it's not symmetrical about the y-axis. It has symmetry, but the axis of symmetry is over here. All right? That one would be neither. Yeah. You want? As soon as it goes left or right, it becomes neither. If it goes up or down, it would still remain even. And children, I'm going to show you an example of another one that's odd that we're going to see often. Yes. Yes. Here's an odd one that you're going to see frequently enough, and I asked you to add it to your parent function list. Do you remember what it was? Close, but 10 repeats. This one doesn't repeat. Just one cubic. Yeah. Okay, so that one's odd. Why? Because you basically just rotated it 180 degrees about the origin. What's up?
Y-axis, it is like odd or even.
Even.
Okay, but it is not. That's odd.
Nope.
Wait, no.
There's three choices.
Okay.
There's even, there's odd, and there's neither. Yeah. Okay? So if it looks like you just reflected it in the y-axis, it's even. If it looks like you rotated it about the origin, 180 degrees, it's odd. If it doesn't look like either, it's neither. Now we're going to do it algebraically. And in 5 minutes, that's when I'll give you your quiz, okay? Well, yeah, you can ask questions, but before we do the algebra, because that's probably the part that you'll have a little bit of difficulty with, the last thing I want to talk about is end behaviors, okay? How does the curve behave when you get close to the end? Well, where are the ends of these curves? Look at the red one. Where does it end going in this direction? Okay, are you talking about x's or y's? Both? when I say go left, automatically you're going to a negative infinity for x. Would you agree? So we don't really care about the x. We care about what's the y. What are the y values doing as you approach negative infinity horizontally? So when we talk about end behaviors, it's understood what the x's are doing. Why? Because you state it. As x approaches negative infinity, so as soon as I say this, I no longer care about the x's. I'm just going to say, this is what the y values do as my x values get closer and closer to negative infinity. Do you understand what I'm saying? So if a curve is doing this, you're approaching whatever y value this happens to be. Maybe this is 0. Maybe it's 1. Maybe it's 2. Maybe it's negative 3. So that's for a horizontal line or a line that's approaching a horizontal boundary or asymptote. What about the red dude? What does the red dude appear to do as we go towards the left? As x approaches negative infinity, what are my red y values doing? What do you think, Apple? Okay, well, the blue one we'll come back to in a second. Cookie, do you know what the red guy's doing? What do you think they're, apricot? Okay, give me a believable y value for this point right here. Whoops. Okay, so you see the point I just highlighted, Atticus? Well, okay, so let's say it's 7. The y value is 7. Now I'm going to go towards the left a little farther. What's a believable y value there? Okay, let's continue. Next one will be there. Correct. So we would say the end behavior is, as x approaches negative infinity, y approaches what value? It may be a value, or it may be a concept. Positive infinity, exactly. Does that make sense? You do. So, because it's usually going to be positive infinity, or negative infinity, or a number. So you usually have 3 choices. That's where we're going with my boy Blue over here. So Apple, you were wondering about Blue, right? My boy Blue? Give me a believable value for the y value for that point. Right there. Well, I went green. Okay, so if that's 3, the y value is 3, as x approaches negative infinity, what's my y value going to do? Give me a believable value there. Apple, this is yours, man. Own it. No? Answer the question. Look, you said that the y value here was 3. What's the y value here? Make it believable. Okay? What? That's believable. What's wrong with you guys? Okay, and we're going to do it again. Apple, what about that dude? No. Make it believable. Well, it could be 2, but it's not 2. So 2.25. And how about this one here? I mean, look more carefully. Anybody want to suggest a number? What? It's probably something like, well, it depends. If you're saying that that's 1, are we saying that that green line, horizontal line, goes through 1? Okay. Well, hey, I didn't write nothing there. Not today, at least. So, yes, if that's 1, then maybe Alex is right. Maybe that's 1.25. And as we get closer and closer to negative infinity, we're going to get closer and closer to what value? 1. What do we call that green lava line? It's an asymptote. So when you have a horizontal asymptote, you'll know from your end behaviors. Usually the curve will approach your horizontal asymptote, maybe in both directions. So for the blue one, we would say as x approaches negative infinity, the y value, in this case we're calling it h of x, is approaching 1. We good? Right on. So we've seen several cases, and if we were going to look at, we did blue, oh, there's only two curves there. All right. Do you guys understand the end behaviors over here as x approaches positive infinity? Okay. So is a function increasing or decreasing? Left to right. End behaviors, you're talking about both ends. So you've got to go to the negative end of infinity and the positive end of infinity. You're only describing the y values at that point. Okay? What's up? Well, the only reason I used h of x here is because on the graph I wrote h of x. But yes, y is. What's up? You don't care about the in-betweens. End behavior, it only cares about the ends. Correct? Yeah, well, it does right here. When you have a horizontal asymptote, you'll approach a number instead of infinity or negative infinity or positive infinity. Okay, so the only other thing that I was going to show you was the algebra part of, but I don't we'll have time, so we'll just skip that till tomorrow. Okay? I got you, Brigitte. Borscht. Okay. You need your pencil, your eraser, and that's about it. You could keep your calculator on your desk, then have your phone handy. I hope